In this unit, we're going to be looking at all things three-dimensional. Exploring solids. A polyhedron is a solid made completely of polygons. Each polygon is called a face. The sides shared between two faces are called edges, and three or more edges meet at vertices. Technically, the plural form for polyhedron is polyhedra. To the left, I have an example of two polyhedra, the classic types that we'd be looking at, which would be a prism and a pyramid. A prism is going to have two congruent bases that run parallel to each other, and then those bases would be connected by parallel edges. Okay, now this actual example is a rectangular prism, so the bases that I could be referring to could be the top and the bottom. Those could be congruent and then connected with these edges here. The bases could also be the right and the left sides here, with them being connected horizontally, or the bases could be the front and the back, which are now connected with these edges that direction. So technically, a rectangular prism can have multiple bases, but in most of the shapes that we'll see, hexagonal prisms, triangular prisms, there's going to be a real obvious base that you'd be using. For a pyramid, you're going to have a single base, which here appears to be maybe a square. Then all the other sides are going to be triangles that meet at a single point, which would be there. We also have solid figures that are not polyhedra. Basically, those shapes are going to have rounded edges somewhere along them. Okay, basic examples would include a cylinder, a cone, and a sphere. For example 1, we're going to decide whether the solid that we see is a polyhedron. If it is, we're going to name it, and we're also going to find the number of faces, vertices, and edges. All right, the first, not much different than what we'd seen previously. This is a rectangular prism, which means that it is going to be a polyhedron. Okay, and the name, of course, is rectangular prism. All right, the number of faces that this has is going to be 6. You're going to have the front, the back, the top, the bottom, the right, and the left. You're going to get 6. The number of vertices that you get is going to be double the number of vertices that you have at a single base. Okay, so if I let the front and the back be the bases, you're going to have 1, 2, 3, 4 vertices, but you also have 4 vertices on the back end as well. So that'll give you 8. To count the number of edges that I have, I'm going to start with counting the edges on one of the bases, which is 1, 2, 3, 4. I'll then double that for the back side here, so that's going to give me 8. And in addition to that, go ahead and add all the edges that connect the bases together, which is another 1, 2, 3, 4. Okay, so that'll give us a total of 12. The second figure is a polyhedron. It is made completely out of polygons. It will be made out of triangles and a hexagon base. Okay, so this will be a hexagonal pyramid. All right, and for the faces on here, what you can do is count the base, obviously, as 1, and then think about the number of sides the bases have. Okay, so if the base here has 6 sides, you're going to have 6 triangles plus that base at the bottom, which is going to give you 7. For vertices, it's going to be 1 greater than the number of sides that you have, which is the same thing that we see for the faces. Okay, so that'll be 7. The edges is actually going to be double the number of sides that you see on the base. Okay, so the base has 6, but you also have the 6 vertices that have those additional edges extending off. Okay, so if we double 6, we get 12. All right, our last figure, which is called a cone, is not a polyhedron. Which means that you don't need to answer the question about faces, vertices, or edges. That would be irrelevant for a figure that is not a polyhedron. In example 1, I gave a little bit of an idea on how you could count the faces, the vertices, and the edges of a polyhedron. In addition to that, there is a nice rule that relates the quantity of those together, which is called Euler's Theorem. Okay, so the number of faces and vertices and edges of a polyhedron can be related using the formula F plus V is equal to E plus 2. The number of faces plus the number of vertices is going to be equal to the number of edges plus 2. So there's that little difference of a 2 here, which is going to be a constant difference. All right, so as an example, here's a picture of a cube. The cube has 6 faces, which we should recognize from a die. The number of vertices that we're going to have are going to be 1, 2, 3, 4 times 2, which is going to give us 8. The number of edges that we'll have will be 1, 2, 3, 4, plus 4 in the back, plus 4 that connect, which gives us 12. And faces plus vertices, 6 plus 8, is going to be equal to the number of edges plus 2, which is 12 plus 2. And that holds true. 14 is equal to 14. All right, for example 2, suppose that we cut a corner off of the cube. Okay, suppose that we just slice off a corner right there. That'll leave a triangular cross-section, show that Euler's theorem still applies. Okay, so if we were to cut this off right here, you would lose that vertice there, but you would gain 1, 2, 3. So you'd lose 1, but you'd gain 3. In addition to that, you would end up gaining 1, 2, 3 edges and 1 extra face that would be there. Okay, so the number of faces would turn out to be 7. You gain that triangular face. Vertices, we start with 8. We lose 1 once we cut that off, so it drops down to 7, but we add on 3 more, which gives us 10. The edges, you don't lose any edges in the process, but you do gain 1, 2, 3, which is going to put us at 15. And F plus V, 7 plus 10, does equal 15 plus 2. Still holds true. All right, and last, just a little bit of fun information. Platonic solids, named after Plato, are constructed with congruent regular polygonal faces with the same number of faces meeting at each vertex. Okay, so here's 5 of them that we get to look at. The first is a regular tetrahedron. Tetra refers to the number 4. We have 4 congruent faces here, which are all going to be equilateral triangles. And at every vertice, we're going to have 3 of those faces meeting up. Okay, the second picture is a cube. Okay, all the sides are going to be squares, which are regular polygons. At each vertice, you have 3 of them meeting up. And third, we have a regular octahedron, octa referring to 8. That is also going to be made out of equilateral triangles, which is similar to the tetrahedron, except that you actually have 8 of them. At all the vertices, you're going to have 4 equilateral triangles meeting up. The fourth picture is a regular dodecahedron, dodeca referring to 12. This will be made out of 12 congruent pentagons. And at all the vertices, you have 3 of those pentagons meeting up. And last, we have an icosahedron, which has 20 faces, each of which are going to be equilateral triangles. At each of the vertices, you're going to have 5 of those equilateral triangles meeting up.
Later, blah.